வாகை சூடவா.
Hello students, today we will discuss on the topic electrostatic potential energy and capacitors. Of all the topics in physics, this is the one among the easiest and interesting topic, as we need not have to apply any vector laws or complicated relations or any drawing free body diagrams. Just what we must know the concept clearly, understand all the formula, and must have the skill in calculating the result. Generally students, mostly 80% of the aspiring students for medicine can solve all the problems in JEE. Only the constraint is time. So to avoid this, we have to analyze the data given, then we have to get the result. For this, we have to use the shortest bridge between the data given and the result. See, we have to choose only the shortest bridge. So in this session, I will help you to find the shortest bridge in arriving the result with the given data. In my session, I will explain a particular concept clearly. Secondly, I will teach you the skill of solving the problem on the content. Okay students. So today we are going to see the first topic is electrostatic potential energy of system of charge. So what is meant by electrostatic potential energy? It's simple. Suppose you are having some charges, one charge and one charge here. To assemble the charges, there will be always a force of attraction or a force of repulsion. Either they will be moving away or they will be either moving closer. Okay, now the first subtopic is electrostatic potential energy of a system of charge. What is meant by the potential energy of system of charge? Suppose if I am having two charges or three or four charges, there is always a force of attraction or a force of repulsion. So to avoid this, to bring the charges in overcoming these forces of attraction or repulsion, some amount of work has to be done in bringing the charges. That amount of work done in assembling the charges from infinity to that configuration, we call it as electrostatic potential energy. Now sums will be based on only two types. Either you will be given system of 3 charge or system of 4 charge. First, initially we will go for the system of 2 charges. So if you are having system of 2 charges, then the electrostatic potential energy is U is equal to 1 by 4 pi epsilon naught into the 2 charges Q1 Q2 divided by the distance between the 2 charges R. In case of 3 charges, the formula, what you have to use the formula? We are having 3 configurations. So U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by the distance R1 R2 plus Q2 Q3 by distance R2 R3 plus the distance Q3 Q1 by R3 R1. This is the most important formula. Based on this formula only, you will be getting many sums. And potential energy is always a scalar quantity. We must have to put the signs. See, be careful students, while for calculations, we must accommodate the sign of the charge. And remember, the potential energy of any charge at infinity is 0. Since electrostatic potential energy of like charge is always positive and potential energy of two unlike charge is always negative. Electrostatic force is always a conservative force. Since for potential we are going to do work against electrostatic force, the potential energy does not depend upon the path, but it depends on the initial and final positions. This is the most important formula students. If you are going to move a charge from A point to the point B, then if you are going to move a charge, suppose I am going to have a charge Q, this charge has to be moved from this point A to the point B. How to do it? The formula is work is equal to W equal to Q into the potential at the final potential minus initial potential, that is W is equal to Q into VB minus VA. Suppose if I am having a system of charges, not 2 charges, I am having a system of charges, you will be asked to find out how much is the work done to bring the charges to that configuration. Simple students, remember the work is you find out what is the potential energy of the final charge configuration, you find out what is the potential energy of the initial charge configuration, you have the difference between these two, that is final potential energy of the charge configuration minus initial potential energy of the charge configuration, that will be equal to the work done to assemble the charges. These two are the most important formulas which we will be often using in calculating the result. Next, the next subtopic is potential energy of a dipole in a uniform electric field. Does a dipole has a potential energy in a uniform field? Yes, definitely. Its formula is U is equal to W into Pe cos theta 1 minus cos theta 2. Sir, what is theta 1? What is theta 2, sir? What is P and what is E? E is the uniform electric field, P is the dipole moment, and what is theta 1 and what is theta 2, sir? Suppose if this is an electric field, this is the electric field, now I am having a dipole, there is some initial angle theta 1. So, to move the dipole from the angle theta 1 to the angle theta 2, some amount of work will be done. So, from theta 1, listen carefully, now the angle is theta 1, to move the dipole from the angle theta 1 to the angle theta 2, the formula for potential energy is U is equal to Pe cos theta 1 minus cos theta 2. Now we are going to find out what is the potential energy of this dipole at an angle theta. So, for this what you have to do, I have to bring this dipole from infinity perpendicular to the field. So, perpendicular to the field means here it is 90. So, U is equal to P into cos 90 minus some angle theta. So, you know very well cos 90 is 0. So, the formula for potential energy at an angle theta is U is equal to minus Pe cos theta. Now, these are the three different positions. The position of 0 energy. So, the position of 0 energy, next position of stable equilibrium, position of unstable equilibrium. What is position of 0 energy? This is the position of 0 energy. What is the position of stable equilibrium? This is the position of stable equilibrium, that is I must have like this. What is the position of unstable equilibrium? I must have, this is the electric field, the dipole is placed anti-parallel, this is the position of unstable. So, in all the cases, the first case in the position of 0 energy, theta 1 is 90, since I am going to move it from perpendicularly and theta 2 is 90 degree. So, the formula for the position for the 0 energy is U is equal to Pe cos 90 minus cos 90, which reduces to 0. For stable equilibrium, theta 1 is 90, I am moving the dipole from infinity perpendicularly. So, 90 to the position theta 2 equal to 0 here. So, U is equal to Pe cos 90 minus cos 0, which is equal to minus Pe. Then work done in rotating the dipole from perpendicular position to anti-parallel position. Here in this case, theta 1 is 90 to the anti-parallel position. So, theta 2 is 180. Now, the formula is U is equal to P cos 90 minus cos 180, which is equal to U equal to plus P. Then work done in rotating, sums will be like this. What is the work done in rotating the dipole from parallel position to anti-parallel position? So, what is parallel position? Theta is 0, anti-parallel position theta is 180. So, U is equal to P into cos 0 minus cos 180, which is equal to 1 minus of minus 1 plus 1. So, answer is U is equal to plus 2E. Okay students, first we will go for the first problem. This is our book back problem. 4 charges plus Q plus minus Q plus Q minus Q are arranged in the corners of the square. Now, they are asking us to find out how much is the work done in assembling the charges. So, definitely these charges would have been brought from infinity. So, definitely we know the potential energy of these charges at infinity is 0. So, we have to find out how much is the potential energy in bringing the charges to this configuration. Since it is a square, I am having, so we have to take the charges plus Q and minus Q, system of charge, and another system of charge minus Q and plus Q, R and S, another system of charge S and Q plus Q and minus Q, another system of charge minus Q and plus Q, and in addition we are having 2 more configurations P and S, that is plus Q and plus Q, and another configuration minus Q and minus Q, they are equal to the distance, the diagonal of the square. So, as explained in the, we are seeing that 4 charges. So, first in our book NEET examinations, you have to crack the answer at a shortest time. So, to find out the potential energy of this configuration, I write as 1 by 4 pi epsilon naught into charge at P and charge at Q by the distance PQ. Similarly, for Q and R, similarly for R and S, similarly for S and P. In addition, you are having two more distributions, charge at P and charge at Q divided by the distance the diagonal PR, plus the charge at Q and the charge at S divided by the diagonal QS. The diagonal is equal to, it's very simple, you apply Pythagoras theorem, you can get PR, it can be written as, or QS can be written as root of x square plus x square, which is nothing but 2x square, which is nothing but x into root 2. So in all the cases you can see 1 by 4 pi epsilon naught into minus Q, you are getting QPS plus Q and QQS minus Q, so I get minus Q squared by x. So in the physical manner you substitute for everything. In the last two steps, QP into QR, QP into QR is nothing but Q into Q squared by the distance root 2x plus QQ into QS. What is QQ? Minus Q. What is QS? Minus Q. Minus Q into minus Q is nothing but Q square, so divided by root 2x. In all the things you are able to see, Q square by x is a common, you take it outside, so you get the answer 1 by 4 pi epsilon naught into Q square by x into minus 4 plus root 2. Now, what would be the initial energy of this configuration? Since this charges has been brought from infinity, their initial configuration would have been 0. Now, work done to assemble the charges, we are having a golden formula. What is the work done to find the, in calculating the charges for a given configuration, final potential energy of the configuration minus initial potential energy of configuration. So, final potential energy of configuration is the calculated one minus 0. So, we are getting this answer 1 by 4 pi epsilon naught into Q square by x into minus 4 plus root 2. Suppose students, you are given, instead of assembling the charges to the square, suppose they are asking what is the work done in dissociating the charges, in disassembling the charges. In disassembling the charges means this is the initial position, final position will be infinity. So, what would be the answer? Here I will be writing final potential energy minus initial potential energy, that is equal to 0 minus of this one. So, the answer will be positive. So, 1 by 4 pi epsilon naught into cube x square plus 4 minus root 2. The same sum you are asked to find out what is the formula to, what is the answer, what is the work done to move 3 nanocoulomb to the center of the charge. To center of the charge means you are going to move the charge from infinity to this point. So, what is the golden formula? Work done is equal to charge into final potential minus initial potential. So, here the final potential of the square, final potential of the square, if you do it, if you add all the charges, the distance is same, in all the charges the distance is same. Charge and the center is same in all the 4 cases, and if you add all the charges it reduces to 0. And what is the final potential? 0. So, work done in moving a 3 micron coulomb to this charge is the golden formula W equal to Q into final potential minus initial potential 3 micron into 0 minus 0, which reduces to 0. Okay, next problem. See students, this is another interesting problem. You are given some charges plus Q plus 2Q minus 3Q assembled at the corners of the triangle. Now, these charges has to be moved to the midpoints of the sides. What is the work done? We know the golden formula. Work done to assemble the charge configuration is potential energy of final configuration minus potential energy of initial configuration. Here the initial configuration is a bigger triangle. In this case, the distance between the charges, equilateral triangle, the distance between the charges is same. So, I can get 1 by 4 pi epsilon naught into this charge Q into 2Q by distance plus this charge 2Q into minus 3Q by this distance plus minus Q into Q by this distance. So, if you solve, you can get it as 1 by 4 pi epsilon naught into minus Q minus 7 by minus 7 into Q squared. What is the final position? Moving these charges to the midpoints. So, this is the position. In this position, the side of the triangle will become equal to x by 2. Since I am moving to the midpoints, the side of the triangle will be equal to x by 2. So, in this case also the same charge configuration, but the distance only is getting varied. So, if you substitute the final potential energy 1 by 4 pi epsilon naught into the same charge configuration, but the distance reduces to x by 2. So, it reduces to 2 by x. If you add, you get 2 by 4 pi epsilon naught x into minus 7 q square. This is the final potential energy. Now, what is the asked question is, what is the work done in moving the charges from the corners to this midpoints? So, formula is W equal to final potential energy minus initial potential energy equal to 1 by 4 pi epsilon naught. Common factor is final is minus 14 q square minus of initial minus reduces to plus. So, the answer is 1 by 4 pi epsilon naught x into minus 7 q squared. The next sum. Now, for this sum, there are given some charges q at 2q and q placed at the corners of the triangle. You are asked to find out what is the relation between capital Q and small q provided the electrostatic potential energy is 0. You know very well, electrostatic potential energy is system of 3 charge, you know 1 by 4 pi epsilon naught into this charge by 2q. So, which reduces to 2q square by x plus another charge configuration 2q into capital Q by x plus another charge configuration q into capital Q by x. So, it reduces to 0 since they are giving that potential energy is 0. So, if you are going to mathematically solve, you can get 2q plus 3q is equal to 0. From this you can get q equal to minus 2q by capital Q equal to minus 2 small q by 3. The same one which I have discussed already. It is somewhat different from the previous problem. Here what they are asking, 4 charges minus q plus 2q and 2q are kept at the corners of the square. You are asked to find out what is the relation between capital Q and small q provided the potential energy at the center is 0. Potential at the center is 0, it is given. So, potential at the center is nothing but 1 by 4 pi epsilon naught into the charge by the distance. Here in this case all the distances are equal. The distance between the center of the square and the corner in all the cases is same. So, I can write 1 by 4 pi epsilon naught into the sum of the charge by the distance is same. So, sum of the charges, you add all the charges. So, if you add all the charges, do the mathematical steps, you can get reduced to capital Q equal to minus q. Next, this is another important problem, children. You are given a charge q, it is placed between two charges capital Q and capital Q at the midpoint. If the system is in equilibrium, you are asked to find out what is the relation between capital Q and small q. Now, it has been given, see listen, charge small q is kept at the midpoint of q capital Q and you take the distance as r and r here. So, the distance between capital Q and capital Q becomes 2r. Now, for this system to be in equilibrium, the potential energy is 0. So, I write 1 by 4 pi epsilon naught into for this configuration q into capital Q by this distance r plus q into capital Q by this distance r plus capital Q into capital Q by the distance here is 2r equal to 0. And if you do the mathematical steps, you can get 2q plus capital Q by 2 equal to 0. From those you can get small q equal to minus q by 4. Okay, students. Next topic is capacitance. What is meant by capacitance? Capacitance is nothing but the measure of an conductor to hold charge. So, many students get confused. What is meant by capacitance? So, to understand the capacitance, I will give a small experiment. So, here I have a LED bulb. When you give a potential difference across the LED bulb will glow. Now, I am having a battery which offers potential difference. If you connect these two, the LED bulb is getting glowed. Now, this is then conductor. Can it offer potential difference? No. So, if we join them, the LED bulb is not glowing. See, the LED bulb is not glowing. So, for this what I do, I am going to connect this capacitor to a battery. So, this capacitor gets charged, it is producing a potential difference. Now, if I connect the LED bulb, the LED bulb is getting glowing. So, this conductor, when the charge is given, it is able to produce a potential difference. The ratio of charge given to the potential is known as its capacitance. Okay, children. So, the capacitance of a conductor, it depends upon the size and the shape of the conductor. Second, it depends upon the nature of the surrounding medium. And third, it depends upon the presence of other conductors near it. In questions they will be asking, will the capacitance of a conductor depend upon the nature of material used? Definitely, capacitance of a conductor does not depend upon the nature of material used, and also it does not depend upon the charge, and it does not depend on the potential developed across it. So, the formula for capacitance is C is equal to Q by V. In case of a isolated spherical conductor, the formula for capacitance is C is equal to 4 pi epsilon naught into R. Children, this is a very important formula. Capacitance of isolated conductor is spherical conductor is C is equal to 4 pi epsilon naught R. So, the capacitance is directly proportional to the radius of the conductor. Now, this is another important problem. 27 identical drops carrying a charge 2 nanocoulomb are placed at a potential of 300 volt. If all the drops combine to form larger drop, find the potential of larger drop. Okay, listen students. So, you are having 27 oil drops, they are combining to form a bigger oil drop. If so, you have to find out what is the potential acquired by this oil drop. The trick in this question is we have to relate this capital R and this small r. See, the volume of the bigger drop will be equal to 27 times the volume of smaller drop, since all of them are identical. So, volume of a sphere is 4 by 3 pi r cube, that is equal to 27 times the volume of the smaller drop. So, from this you can get r is equal to 3r. After arriving there, this is the main trick in this question. We are going to compare the relation between the radius of the oil drop, bigger oil drop, and the radius of the smaller oil drop. Next, we know very well capacitance of a isolated charge is directly proportional to the radius. So, in this case, its capacitance I will have it as C, its capacitance I will have it as C dash. This capacitance is proportional to R, its capacitance is proportional to capital R. This capacitance is equal to, I can write as K into R. Here I can write as C dash equal to K into capital R. This is another trick, second trick. I am comparing the capacitance of the smaller drop to the capacitance of bigger drop. You can see that the radius of the bigger drop is equal to 3 times the radius of the smaller drop, and if you divide this C dash and C, you can get it as C dash is equal to 3 into KR. Now, what is the charge on the smaller drop? Q equal to, general formula for Q is equal to C into V. So, V equal to C can be written as K into R into the potential of the smaller drop is 300, that is equal to 300 into KR. Now, what is the charge on the bigger drop? Q dash, that is equal to 27 times the charge of the smaller drop. So, 27 into KR, that is equal to into 300, it reduces to 8100 KR. Now, the formula for potential of the bigger drop is V dash is equal to Q dash by C dash. So, if you divide these mathematical steps, you can get potential of the bigger drop as 2700 volt. Now, isolated conductor capacitance. Now, I am going to increase the capacitance of an isolated conductor. What we have to do? We have to bring another earthed conductor near it. Such an arrangement is called as capacitor. The capacitance mainly depends on size, shape, relative position of two conductors, and the nature of medium between the two conductors. In our lesson, we are having parallel plate capacitor. What is a parallel plate capacitor? It consists of two large plane parallel conducting planes separated by a small distance. So, in the beginning itself I told the capacitance is a very easy topic. You have to understand the formulas clearly. So, here these are the important formulas. The electric field between the two plates will be equal to E is equal to sigma by epsilon naught, that is Q by A into epsilon naught. The potential difference between the plates will be equal to E into D, and the capacitance of a parallel plate capacitor C is equal to Q by V, that is equal to epsilon naught A by D. So, clearly capacitance depends upon the nature of the medium, the distance between the two plates, and the shape of the conductor A. Now, students, now we are going for another important topic. Based on this topic only, we will be getting most type of sums, capacitors in series and capacitors in parallel. In case of capacitors, what is meant by capacitors in series? You are seeing the diagram, you are able to see 3 capacitors. This arrangement is given a potential difference V. See, are all the plates getting this positive potential? No. This first capacitor, this first plate is getting positive potential. So, this type of connection is known as series. Whereas, look at this type of connection. Look at all the capacitors. See, all the plates receive positive. this first capacitor receives positive, second receives positive, third receives positive. Similarly, the lower plate of the capacitor C1 gets negative, negative, negative. So, this type of connection is known as capacitors in parallel. So, in capacitors in parallel series, source charge is always constant, potential differences vary V1, V2, V3, whereas in parallel the charge stored is different, whereas the potential is constant throughout V, V, V. Now, in case of capacitors in series, the effective capacitance formula is 1 by Cs is equal to 1 by C1 plus 1 by C2, so on like that, whereas in case of parallel, it is Cp is equal to C1 plus C2 plus so on. Students, now we are going to go for important formulas. If you are given two capacitors in series, then the effective capacitance formula, simple formula, trickiest formula, you go for it, Cs is equal to C1 C2 by C1 plus C2. If they are in n equal capacitors, n equal capacitance series, the effective capacitance Cs is equal to C by n. In case of two capacitors in parallel, Cp is equal to C1 plus C2, and in case of n equal capacitors, the formula is Cp is equal to n into C. Clearly you can see Cs is always less than the individual capacitance, Cp is always greater than the individual capacitors. So, these are the important concepts. Cs is always less than the individual capacitance, Cp is always greater than the individual capacitance. Next, we are going for the effect of dielectric. What will happen to the capacitance of a capacitor when a dielectric is introduced? So, in case of air filled capacitor, its formula is C is equal to epsilon naught A by D. In case of the capacitor being filled by a dielectric of dielectric constant epsilon r, in CBSE books they are writing it as K. In some in NEET exams also they are writing the relative permittivity as K. So, I have given both the formulas. C dash is equal to, instead of epsilon naught I must add extra additional term epsilon r epsilon naught A by D, or otherwise K into epsilon naught A by D. For any dielectric, K value is always greater than 1. No material in this world has a dielectric constant lesser than 1. So, all materials has a dielectric constant K greater than 1. So, what happens? The net effective capacitance will get increased. So, whenever a dielectric material is introduced between the capacitor, its capacitance will increase. Next, energy of a capacitor. You would have learnt energy of a capacitance is Q square by 2C. The same thing, energy of capacitance is half CV squared. When you have to use these things, if charge is constant, you go for this formula UB equal to Q squared by 2C. If V is constant, go for this formula half C V squared. Next, energy density of a capacitor, that is energy stored per unit volume in a capacitor is UE is equal to half epsilon naught E squared. So, in this, the main trick here is the capacitance will increase when a dielectric is kept inside the capacitor. Okay, students, the next content is what happens when a dielectric is introduced into a capacitor after charging and then after removing the battery. So, in this first case, when the capacitor is charged by a battery, the charge is Q naught, potential difference is V naught, electric field is E naught, its capacitance is C naught, and the stored energy is U naught. Now, when you remove this battery and when you are filling this capacitor with a dielectric, the charge remains the same. Initially, what was the charge Q naught? The same charge will remain, but what happens? The potential difference will decrease by K, V naught by K. Electric field also will decrease, E naught by K. Why K is always greater than 1, so definitely E will be less than E naught. Capacitance will definitely increase, C dash is equal to K into C, and the stored energy, what will happen? Its stored energy will get decreased, U is equal to U naught by K. Since the formula for U is half CV square, so V is getting decreased, so I am getting as U naught by K. So, when you remove the battery, the stored energy gets decreased, but when you reconnect the battery once again, what happens? The charge increases, Q equal to K into Q naught. I am getting the same potential difference, V is equal to V naught. Electrical field is constant, E is equal to E naught. Children, carefully listen. Then also capacitance will increase, C dash is equal to K into C, and the stored energy will increase, U is equal to K into Q naught. So, when the battery is removed, stored energy gets decreased. When the battery is once again reconnected, stored energy increases, U is equal to K into U naught. This This is an important concept you have to understand. Okay. Now, based on this, now we will be seeing sums. What are the previous year questions? What are the opportunities for the questions to be asked? In this question, a Palpate capacitor is connected to a cell and then it is getting disconnected and a dielectric slab is getting introduced. Of the following options, which is the correct one? Which is the incorrect one they are asking, not the correct one, incorrect one. So, you can see potential when the battery is removed, you know very well the potential difference gets decreased. So, C is right, potential stored energy gets decreased, answer so D is right. And what happens, what is the A? Change in energy. What is the change in energy? Ui minus Uf. So, what was the initial energy? C V square by 2. What was the final energy? C V square by 2k. So, what will be the energy, change in energy? C V square by, if you take C V square by 2 as a common, you can get C V square by 2 into 1 by k minus 1. So, A is also right. Now, look at the option B, the charge on the capacitor is not conserved, but we know very well children, when the battery is disconnected, the charge remains same, the table. So, B is the right answer, that is the incorrect one. Charge is always conserved, here they are giving charge is not conserved, so B is the right answer. Okay, next problem. Then the next content. Sums are asked based on these questions also. When two charged capacitors having different capacitance are joined in parallel, two charged capacitance having different capacitance, they are joined in parallel, there is definitely loss in energy. Why? So, see in the diagram itself I given, I am giving a capacitance C1 connected to potential difference V1, so it possesses a charge Q1 equal to C1 V2. Another capacitor C2 connected to a potential V2, it acquires a charge Q2 equal to VC2 into V2. Now, when the two capacitors are put in parallel, they acquire a common potential. That common potential formula is V is equal to C1 V1 plus C2 V2 by C1 plus C2. Children, please make this formula important. Sums are often we are getting sums based on this common potential V equal to C1 V1 plus C2 V2 by C1 plus V2, and definitely there is a loss in energy. You can see the initial energy is this much minus final energy. What is final energy? Half into parallel, so C1 plus C2 into V square, this common potential. Definitely if you do the mathematical part, the initial energy will be always greater, there is a loss in energy, that loss in energy is half into C1 C2 into V1 minus V2 whole square by C1 plus C2. Okay. Now, we will go for the sums. Look at the diagram children, you are given the circuit, you are asked to find out what is the value of C if the effective capacitance between A and B is 1 by 2 micron farad. So, instead of this part, I have to get a single capacitance. That single capacitance into C connected in series, that effective capacitance must be 1 by 2 micron farad. So, now we will see these two capacitors are in series. So, what is the formula? Cs is equal to C by N. C is 2, how many capacitors are there? 2, C by N, 2 by 2 which is nothing but 1. So, in place of these two I can have only 1 micron farad. Look at these two, this is 1 and this is 1, both of them are in, they are also equal. So, 1 and 1 they are in parallel. So, what is effective capacitance? Cp is equal to N into C, number of capacitors 2 into 1 which is nothing but 2. Look at these two are in parallel, 2 and 2 they are in parallel, equal capacitance. So, what is the effective capacitance? Parallel, Cp is equal to C1 plus N into C, 2 into 2 is nothing but 4, in place of these two I 4. Now, look at these two, 2 and 4 they are in series. So, for series what is the formula? C1 C2 by C1 plus C2. So, 2 into 4 by 2 plus 4 is nothing but 6, 8 by 6 which is nothing but 4 by 3. So, in place of these two I can have only one capacitor 4 by 3. Look at these two, they are in series. So, what is the area also equal? So, Cs is equal to C by N, Cs is equal to C by N. So, 2 by 2 which is nothing but 1. So, instead of having these two capacitors I can have only 1 micron farad. Now, look at this 4 by 3 and 1 they are in parallel. So, instead of these two capacitors I can have single capacitance Cp is equal to C1 plus C2 4 by 3 plus 1 which is nothing but 7 by 3 micron farad. So, instead of these two capacitors, I can have only one capacitor 7/3 micron farad. Now, they are given Cs is equal to 1/2 micron farad. So, we know 1/Cs is equal to 1/C1 plus 1/C2. 1/Cs is nothing but 2, 1/C1, what is 1/C1? C, plus what is 1/C2? What is C2 here? 7/3, which is nothing but 3/7. On solving, we can get the capacitance as C is equal to 7/11 micron farad. Okay, children, this is the sum which I have discussed previous session. Now, in this circuit, they are giving what is the given circuit, what is the charge flowing through this 4 micron farad. 1 and 5 are in parallel. So, now listen. So, instead of 1 and 5 micron farad, what you can do? So, listen, the two capacitors are in parallel. So, the effective capacitance Cp is equal to C1 plus C2, which is nothing but 1 plus 5, which is nothing but 6 micron farad. Now, 4 and 6 are in series. 4 micron farad and 6 micron farad are in series. So, their effective capacitance is C1 C2 by C1 plus C2, which we reduce it as 2.4 micron farad. So, now 2.4 micron farad and 3 micron farad are once again in parallel. For parallel connection, potential difference is same. So, for 2.4 micron farad also, the potential is same, 10 volt. So, what is the charge flowing through for 2.4 micron farad? Q equal to C into V, 2.4 micron into 10, which is nothing but 24 micron. So, now we go for the previous circuit, 2.5 micron farad. From where we are getting this 2.4 micron farad, 4 and 6 were in series. So, we got the effective capacitance. Now, the charge flowing through 2.4 micron farad is 24 micron coulomb. Then definitely, since 4 and 6 are in series, same charge would have been flown through 4 and 6. So, the charge flowing through 4 micron farad is 24 micron coulomb. Okay, next problem. In this case, I told you a golden formula, the common potential, no. Based on that, we are going to see a formula. A capacitor is connected to a battery, the battery is removed, and we are going to join it to another identical uncharged capacitor in parallel. What happens to the electrostatic potential of the system? So, you see the capacitance C, it is charged with a potential V. I am having another uncharged capacitor, so V is equal to 0. So, what is the initial energy of this capacitance? Ui equal to half CV square. After connecting this capacitor to this uncharged capacitor, the common potential is C1 V1 plus C2 V2 by C1 plus C2. This is a golden formula. So, in this case V2 is 0, so I can get it as CV by 2C, which is nothing but V by 2. So, the common potential of this parallel arrangement is V by 2. So, what would be its capacitance? So, what would be its effective capacitance? They are in series. So, C plus C, which is nothing but 2C. So, what is the final energy? UF is equal to half CV square, half 2C into V square, V by 2 common potential square, V by 2 whole square, that reduces to half CV square. You can clearly see it is nothing but half of initial energy, half into half CV square. So, Ui by 2, so that decreases by a factor 2. Okay, next problem. In this case, the same thing here also. A capacitor of 2 micron farad is charged. When the switch is moved to S, what is the percentage of energy dissipated? So, when the switch is connected to 1, the capacitor is getting charged. So, its electrostatic energy is half CV square, half into 2 into V square, that we can write is 2 into 2. Its capacitance is 2 micron farad given. 2 by 2 is nothing but V square. No need to put micron, since we are asked to find out the percentage of stored energy only. So, later on it will be getting cancelled. So, it is V square. When S is connected to 2, it is getting connected to uncharged battery. So, the common potential is C1 V1 plus C2 V2 by C1 plus C2, and here V2 in this case V2 is 0. So, I am getting V by 5. So, in this case, what is the final electrostatic energy? Half into, they are connected in series, they are connected in parallel. So, C1 plus C2 into V square. So, 2 plus 10, which is nothing but, so 2 plus 8 is nothing but 10 into common potential is V by 5. So, V square by 5, V square by 5. So, this is the final electrostatic energy. They are asking what is the percentage. Children, generally percentage of change, there will be a formula is change by original value into 100%. If you are asked to find out percentage of change or percentage of decrease or percentage of increase, simple formula is what is the change by what was the initial value into 100%. Now, in this case, what is my change? Ui minus Uf. So, V square minus V square by 5 by what is the initial value? 5 square into 100%, it reduces to 4 by 5 of 100%, which is nothing but 80%. Okay. Next question. Students, so diagram like this. In this, the plates between the two capacitors are filled by 4 dielectric material K1, K2, K3 and K4. Now, instead of having 4 dielectric material, I want to have a single dielectric material. What would be its dielectric constant? This is the question. Now, look at these three capacitors. This is connected. Suppose I will have this as positive. This is connected to negative. Look at these plates. This plate is connected to positive. This plate is connected to positive. This plate is connected to positive. So, these three capacitors filled with dielectric K1, K2, K3 are in parallel. So, these three capacitors, since all these three this plate is connected to positive, this plate is connected to positive, this plate is connected to positive, all of them are in parallel. Now, this capacitor that is connected in series with these 4 capacitors. So, I will have it like this. So, this is C4 who is filled with the dielectric constant K4. Now, you see, I will find out the capacitance of this one. Since all of them, the area, the total area is getting divided. So, its area is A by 2. Its area, the total area is divided by 3 capacitors. So, its area is A by 3. Area is A by 3, A by 3, A by 3. And this area, what happens to this area? This is A by 2. Is it clear, children? And what is this distance? D by 2. What is this distance? D by 2. So, now look at this question. This diagram, capacitors, they are filled with the 4 capacitors K1 of different dielectric material K1, K2, K3 and K4. What is the effective capacitance they are asking? What is the effective dielectric material which has to be used? So, for the first capacitor, the area is A by 3, second one A by 3, third one it is also A by 3 and the total distance is D. So, in this case, what is K1 here in this C1? Formula is K1 into epsilon naught K into epsilon naught A by D. So, K1 into epsilon naught, here the area is A by 3 into distance is D by 2, D by 2. So, it reduces to 2 K1 epsilon naught A by 3D. For the second capacitance, the same thing you will be getting, the dielectric material is different. So, K2. For the third capacitor, you will be getting the same thing, the dielectric material is K3. But for the fourth one, C4 is equal to K4 into epsilon naught A by the distance is D by 2. So, you will have it as, now the next question. Now, we are given 2 diagrams. The 2 diagrams, it is filled with 3 dielectric material K1 of dielectric material constant K1, K2 and K3. Here in this case, if you look at these 2 diagrams, first diagram, K1, K2 and K3, all the 3 capacitors are connected in series. So, what is the capacitance of the first capacitor? C1 equal to K1 epsilon naught, area is same A by the distance. So, the distance D is shared by the 3 capacitors, so the distance becomes D by 3. So, it reduces to 3 K1 epsilon naught A by D. The second capacitor, the same arrangement, the thing is that the dielectric constant is different. So, I will have it as K2. For the third one, I will have it as the dielectric constant is dielectric constant is changing. So, I will have it as K3. Now, all the 3 capacitors are connected in series. So, 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. If you do some mathematical steps, I am getting this one. 1 by Cs is equal to D by 3 epsilon naught A into K1 K2 K1 K3 plus K1 K2 by K1 K2 K3. Now, in the second diagram, look at the arrangement. The 3 capacitors are in parallel K1, K2, K3. So, in this case, what happens to the capacitance? K1 equal to K1 into epsilon naught. The area of the plate is shared by 3 capacitors. So, the area of single capacitor is A by 3 by D. So, it reduces to K1 epsilon naught A by 3D. For the second capacitor, just change the dielectric material K2. For the third capacitor, take it as K3. Now, all the 3 capacitors are connected in parallel. So, Cp is equal to C1 plus C2 plus C3. So, if you add these 2, I am getting epsilon naught A by 3D. Now, we will find out what is Cs by Cp. You divide, we have already found out Cs and we have already found out Cp. You divide these 2 with the ratio of Cs and Cp is, I am getting this answer, 9 into K1, K2, K3 by this denominator whole divided by K1 plus K2. The question asks this, what is the ratio of the energy stored in these two diagrams, these two circuits. So, energy you know very well, they are given the constant potential. For constant potential, what formula is used? C is equal to half C V square. So, energy is directly proportional to capacitance. So, US by UP is equal to this CS by CP, which is nothing but this answer. Next one, look at this arrangement. 3 capacitors are given, material K1, K2 and K3. They are different, separated by some distance 3 millimeter. If you have to replace all these 3 capacitance by a single dielectric material of K, what is the value of K? That has been asked. K1, K2, K3 has been given. Now you see K1, K2, K3. All these plates, upper plates are receiving positive. All the lower plates are receiving negative. So, all these capacitance are connected in parallel. So, I will find out the capacitance of each one. Capacitance formula is K into epsilon A by D. K1 epsilon A by 3 by D. Why I am getting A by 3? Area of the total area is divided by the 3 capacitors. So, I will have it as A by 3. So, it reduces to K1 epsilon A by 3D. For C2, change just only the dielectric constant. C3, change only the dielectric constant K3. For the if single capacitance, I must have the dielectric constant as K. Now, since these 3 capacitors are connected in parallel, the effective capacitance is C1 plus C2 plus C3. You substitute, epsilon A by D get cancels. So, I am getting K equal to K1 by 3 plus K2 by 3 plus K3 by 3. If you substitute the numericals, I can get K equal to 12. Okay, children? Okay, next. Now, this is another problem based on common potential. 2 capacitors C1, C2 connected to 120 volt to 200 volt. It is found that after connecting them, the common potential is 0. Then what is the relation between C1 and C2? They are asking. Now, it has been given common potential is 0. So, common potential formula, the golden formula, C1 V1 plus C2 V2 by C1 plus C2, that is equal to 0. So, from the C1 V1 plus C2 V2 equal to 0, substitute the value of V1, V2, do some manipulation, we get 3 C1 equal to 5 C2. So, the answer is B. Next question. Next, children, it is a very important diagrammatic question. Now, in this diagram, they are giving, I am having 2 capacitors. The 2 capacitors were joined in series and they were joined in parallel. The effective capacitance has been shown in A and shown in B. We do not know whether A is series or A is in parallel. Similarly for B also. So, we are going to find out what are the individual capacitance C1 and C2. See, generally in this one, here the x axis I am having V, the y axis I am having Q. The ratio of Q by V, which is nothing but the slope of the curve, will give you the capacitance. So, the slope of the curve gives you the capacitance C is equal to Q by V. Now, look at this value, look at the two diagrams A and B. The angle between x axis and A is larger. So, its slope is larger. So, slope of A is larger. You know very well which will be greater, CP or CS. CP will be always greater than CS. So, definitely A represents CP and B represents CS. So, slope of A, so I will find out the slope of A. So, the value is 500, here it is 10. So, slope of A is 500 by 10. It will give you CP or CS? CP. Why? Slope of A is greater. So if CP only is greater than CS, so CP is equal to 50. CP is C1 plus C2 equal to 50. Next, slope of B, 80 by 10, which is nothing but CS is equal to 8. So, B curve represents which one? CS or CP? CS, since its slope is lesser. So, CS is equal to 8. CS formula is C1 C2 by C1 plus C2, that is equal to 8. Then you have C1 plus C2 equal to 50. You solve it, C1 C2 equal to 400. So, you are having C1 plus C2 is equal to 50. So, you are having C1 C2 is equal to 400. We have seen many sums like this. On solving these two, using some quadratic equations, I am getting the value of C1 and C2 as 10 microfarad and 40 microfarad. Is it clear, children? Okay. The next one. This is the sum where you have to use apply vector laws. So, listen, a simple pendulum of mass m, it is oscillating between the plates of a parallel plate capacitor. It is having some charge. You have to find out what is the time period of this simple pendulum. Time period formula is, we know very well, T is equal to 2 pi into root of L by G. So, in this case, we have to find out what is the acceleration. Since this charged ball is oscillating in between the plates of a Palpate capacitor, it experiences two types of acceleration. One, the acceleration due to gravity which is acting vertically downwards. Second, the acceleration due to the electrical field which will be acting horizontally between the plates. So, A is equal to force by mass, force is EQ by m. So, I am getting the acceleration due to the electric field is A is equal to EQ by m. Now, I am getting two accelerations, one G acting downwards, another A acting horizontally. The resultant of these two vectors, when two vectors are acting perpendicular, the resultant formula is R is equal to root of first vector square plus second vector square. So, in this case root of G square plus that A square is nothing but EQ by m whole square. So, my resultant acceleration is A is equal to root of G square plus EQ by m whole square. Time period formula is T is equal to 2 pi into root of L by G. Instead of G, I will have it as resultant, acceleration resultant. I am getting the answer like this. Is it clear, children? Okay. The next one. It is a simple question. Electrostatic between the plates of isolated capacitor C having a charge Q area is what happens to the electrostatic force? Force between the metal plates. We have a formula F is equal to Q square by 2 epsilon, 2 epsilon. Here force is independent of the distance and all other options are incorrect. Okay. Okay. Next, here you are given the capacitance C, D is the distance is D, potential difference is V. What is the force of attraction between the capacitors? See, if I am having two capacitors, one plate, another plate, to move the, what is the force? They are asking what is the force between these two plates. So, to move the plate from one point to this point to a distance D, the work done is equal to F into D, isn't it? To move one plate from another plate, I give a force. That force will be equal, that force into the distance moved will give you the work done. That work done will be equal to the change, that work done will be equal to the electrostatic potential energy. So, if I apply this work is equal to electrostatic potential energy, F into D is equal to half CV square. In place of potential energy, why I am using half CV square? Here they given the potential difference here is constant. So, I use half CV square, not Q square by 2C. So, F is equal to CV square by 2D. So, the answer D is right one. Now, this is an interesting sum. You are given 4 diagrams and in this diagram you are given 2 dielectric material of K1 and K2. K2 is greater than K1. Of these diagrams, which is correct? That is, when the distance is varying, what happens to electric potential difference? Now, you see clearly, when the dielectric is introduced, what will happen to the electric field? Electric field will decrease. Electric field will definitely decrease. When the dielectric constant is more, electric field will decrease largely. So, as I move from the plate, first I am having air. So, the value of E is constant. Next I am moving into the area of dielectric constant K1, its value is slightly lesser. So, its electric field will decrease. Next I am moving into the middle air, potential electric field is constant. Next I am moving into another dielectric of dielectric constant K2 greater than K1. So, electric field will decrease to a large extent. So, in the figure C of the of the 4 options, the figure C represents the exact answer. Next, you are given 7 capacitors of capacitance 2 microfarad. They are to be connected in one configuration, so that the effective capacitance must be equal to 10 by 11 microfarad. How to approach this sum? So, I will assume that I am going to have n capacitors in parallel and 7 minus n capacitors to be in series. So, what is the effective capacitance of n parallel capacitors? Cp is equal to Nc. So, n is unknown, C is known 2, so 2n. Effective capacitance of 7 minus 1 n equal capacitors, Cs is equal to C by n. So, 2 by 7 minus n. So, number of capacitors is 7 minus n. Now, these two arrangement are once again put in series. So, effective capacitance is 1 by Cp, C effective is equal to 1 by Cp plus 1 by Cs, and 1 by Cp, 1 by C effective is 11 by 10, 1 by Cp is 1 by 2n plus 1 by Cs, you reverse it 2 by 7 minus n, that is nothing but 7 minus n by 2. We are doing some mathematical part. After doing the mathematical part, I am able to get n value as either 50 by 10 or minus 2 by 10. Minus 2 by 10 is a negative value, I can neglect it. So n is equal to 5. So n is of acceptable value. So 5 capacitors has to be connected in parallel and 2 capacitors has to be connected, that is 7 minus 5, 2 capacitors has to be connected in series. Is it clear, children? Okay. Now the last one. Okay, students. Now we will see, we are given a circuit like this. We are asked to find out what is the effective capacitance between x and y. So we have to redraw this circuit. I will have this point as A. So this I am getting A for this plate. I will have this as D. So I am getting D here. This is no, I am not getting any point here. So I will have it as B. Here also I am having a no point. I will have it as C. So it is connected to C. This is connected to C. This is connected to B, and this is also connected to B. Look at this capacitor, this is connected to C and this is connected to D. So we are having how many points? 4 points. A, D, next we are having B here, next we are having C here. Now connect all, each and every one. Look at this capacitor A, B, it is to be connected to A and B, 6 micron farad, 6 micron farad, over. Next go for this one, between A and C, this one, it is 6 micron farad, over. This one is also over. Now go for this one, it is connected between B and C, it is B and C, 20 micron farad, which is B and C, 20 micron farad, over. Now go for this one, connected between C and D, 6 micron farad, this also over. Now go for last one, B and D, 6 micron farad, B and D, 6 micron farad. So A is connected to X, D is connected to Y. Now does it looks like a Wheatstone's network? Capacitor also follows Wheatstone's network. What does Wheatstone network tell us? It tells us top capacitance by top capacitance must be equal to bottom by bottom. Is the condition satisfied? Yes. 6 by 6 equal to 6 by 6. So the bridge is balanced. So I can remove this capacitor. No charge will flow through this capacitor. Now you see these two are connected in series. Instead of single capacitance, I can have a single capacitor, two capacitors of equal value. Cs is equal to C by N, 6 by 2, which is nothing but 3 micron farad. Look at these two are connected in series. So Cs is equal to C by N, C value is 6, 2 capacitors are there, so I will have it as 2. 6 by 2, which is nothing but 3. Now 3 micron farad and 3 micron farad are connected in parallel. What will be the effective capacitance? Cp is equal to N into C. So 2 into 6 is nothing but, so the effective capacitance is 6, 2 into 3, 6 micron farad. So between the points X and Y, the effective capacitance is Cp is equal to 6 micron farad. Is it clear, children? Okay. So in this session, what all we have seen? First we have seen the potential energy of system of charges, and next we have seen what is the potential energy of a dipole in an electric field, and based on those two topics we have seen some important problems. Third, we have seen the capacitance of a conductor, and next we have seen capacitance of a capacitor. Then we have seen capacitance in series and capacitance in parallel. Then we have seen effect of dielectric in affecting the capacitance of a capacitor. So these are all the concepts which we have seen, and we have seen some problems also based on those things. So I wish you students, if practice makes a man perfect. So practice sums like this: practice, 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 you will get success. Thank you.
இந்நிகழ்ச்சியை பற்றிய தங்களின் மேலான கருத்துக்களை கீழ்க்கண்ட முகவரிக்கு கடிதம் மூலமாகவோ மின்னஞ்சல் மூலமாகவோ குறுஞ்செய்தி மூலமாகவோ தெரியப்படுத்தலாம். அனுப்ப வேண்டிய முகவரி சிறப்பு அலுவலர், கல்வி தொலைக்காட்சி, 8ஆம் தளம், அண்ணா நூற்றாண்டு நூலகம், காந்தி மண்டப சாலை, கோட்டூர்புரம், சென்னை 6,85,000. தொலைபேசி எண் 7824015000.